Good morning, everyone. These are instructions to complete this online lab activity. I would like to have you guys working at home, and as I mentioned, this past Monday, I will use the time on Monday to go over class notes and homework, problem solving, and solving other problems as we go. So once you log in Moodle, so you log in Moodle and then find your class, Physics 2A, scroll down to March, the week of March 2, and then we have a file in there. Click on it, and this is your handout. This file I just borrowed from Fat Colorado. So you write your name in there, the date, and then you have to write a definition of Newton's 3 law, what frictions are, what is static and kinetic. So try to be brief about it, and pretty much that's it. So if you click on this link, it should take you to Fat Colorado. Otherwise, if you Google Fat Colorado, you will easily find their web page, and then you play with simulations, find physics, find motion, and so we have several options, and what we want is forces and motion bases. So click on it and then click on Run Now. You can run in HTML. It works for tablets. I have a PC here with me, so I'm going to do that one. It's coming in. So click Run. Depending on how the security of your computer goes, it might come up with a yellow warning bar asking you if you want to download or not, so just accept it. I think the best thing to do first is just to play around with the system itself. You can bring people in here. So if you have a card and you have no one pull on it, the card's not going to move, right? So, but if you have somebody pulling, that's going to make it move. So I think we all have that. We all have that experience before. So we can bring another person in there. If the two forces pulling on the card have the same intensity, the same magnitude, but as you expect, the red dude is going to pull to the other side, these two forces cancel out, so the card doesn't move. So as we saw on Monday, last Monday, net force equal ma, remember that? It's Newton's second law. So if net force, which means negative blue force plus positive red force, they both have the same number. One is positive, the other is negative. Let's say -4 plus 4. When you add those two numbers, you get 0. 0 is equal ma. So acceleration is 0, there is no motion. Okay? Unless you intensify, you know, and then you're gonna you can play around with frictions too. So in fact you can play around with motion. So we put a little girl there, and then you apply a force of whatever number of newtons. Let me repeat this. So you have a robot, and you're gonna put a little girl sitting there. Force applied is 0. There is no motion. Now let's apply a little force on it. So you see the girl is accelerating, right? Because there is an applied force on it. Force is equal ma. With an acceleration given, the velocity, in this case also speed, keeps on growing, 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 growing. If you stop applying the force, oops, now she moves. She keeps on moving, but with constant speed. Let me reset this. And you really should play with that before you start anything. So the girl is there. I want to see speed. And I'm going to apply a force. 3 newtons. How about 45 newtons? I'll keep applying. So look at the speed. The speed is growing because since there is a net force that is not 0, acceleration is not 0. And as we learn in laws of motion, if there is an acceleration, the speed changes. Or in other words, the velocity changes, to be more precise. So if I stop the force, the speed remains constant according to Newton's law. This girl is going to be moving forever and ever with the same speed unless a net force different from 0 is acted on her. So in reality, in our real life, this never happened because there is something called friction. So bring a can, apply force. Now there is static friction. See that? Static friction is when you apply the force, but the static friction matches that force you apply. Up to a point, static friction can't handle anymore. And then motion starts. And when that happens, instead of talking about static friction, we talk about kinetic friction. So, and once you stop applying the force, kinetic friction will be the one responsible for stopping the motion. So you can bring values into consideration. I have friction, right, playing a role in here. Let's do the same. Now, kinetic friction does not change because it's equal to a coefficient times the normal force, remember? So if the applied force overcome, which is 203 newtons, overcome the kinetic friction, the net force is positive 203 minus 125. That net force is proportional to the acceleration. The acceleration will be the one increasing the velocity value up to the point you can't handle anymore, and then you fall down, and static friction now acts on the motion, providing a negative acceleration. You have a slowing down process, and the trash can stops. So play with this, and then let's take a look at the handout. The handout can be found in here, right? So this is what we did. We spent a few minutes familiarizing with the simulations, so on, so on, so on. So let's play with the friction. Click on the friction tab as we did, check all boxes, this and that, place a 40 kilograms girl on the screen, type in the box to have a 150 newtons force on it. And then you have to complete this table. So you apply a force of 150 newtons. What is the value of a normal friction? What's the weight of the object? In other words, what is the normal force? In this case, the weight is equal normal force. So when you plot a graphic here, you have to use your Excel spreadsheet. So email me if you don't know how to use your Excel spreadsheet, and I will put up a tape for you or for the class. If I don't hear from the students, I understand you know how to use your Excel spreadsheet to determine, to tally, to translate this table and put in Excel spreadsheet so that you can calculate this slope and find out what that slope means. Okay, that's the first part. The same thing with acceleration. This should also result in a graphic, and you have to interpret the slope of this graphic. Okay? And write a conclusion. So this is the author of this handout. It was not me. Alright? Good enough? And then bring me on Monday. I would need that for Monday. Oh, my ear, now that I'm seeing the screen isn't showing up for me. Oh, you know what? It's because I was taking out. I was disconnected and brought it back. And so when it brought it back, it disconnected my screen. Sorry about that. And I didn't see it. But so basically, I'm taping this and I'm putting in Moodle. You should be able to see it and follow. Okay, all right. But basically, you go to FET Colorado, find the simulation and play with it. Play with friction, tug war. That's the simplest one. So it kind of explains you what the net force is, right? Also explain what motion is. That's a slowing down process when the force applied is against the direction of motion. This is a speeding up process when the force applied, the net force applied, is in the direction of motion. Okay. In this example, the girl is keeping moving with the same speed because friction is none. There is no friction in there. But in a real life situation, if you apply a force on it, the speed will keep on growing, 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 growing. And once you stop applying the force, um, the kinetic friction is responsible for slowing down and bring it to a halt. Okay. So play this simulation, and which helps you to visualize how force and acceleration play together in the process of explaining motion, and and how problems can be solved that way. So I'm gonna take I still have some 30 minutes to go, and what I will do, I will pause the taping. Start all over. Oh geez, I didn't tape two problems. That's too bad. For those of you following this, I'm doing problem number 10. Is a bullet that is coming out of a rifle, and is asking for the average force on it. The mass of the bullet is given, and the net force is the force that the chemical reaction expelling the bullet is responsible for. And so that is equal ma. Mass is given, so force can be determined as long as we know acceleration. So I'm in the process of finding out the acceleration. I know three equations of motion as long as acceleration is uniform: position versus acceleration in time, velocity versus acceleration in time, and Bernoulli. So I know the final velocity, the velocity in which the bullet leaves the barrel, 320 meters per second. So I'm using this information to solve my problem. So 320 square is equal initial velocity square plus 2 times acceleration times final position minus initial position. So when you take your x-axis going this way, final position 0.82 minus initial gives you 0.82. So from here we can determine our acceleration. 320 square divided by 2 times 0.82 meters per square second. And once you take this value, plug it in there, and you can find your force. Okay? Take a look at another problem that involves forces and how about number 12? You have two forces that are applied to a car in an effort to move it, as is showing here. So you have a 450 newtons force that is applied with an angle 10 degrees, and a 400 newtons force that is applied with an angle 30 degrees with respect to, to the forward direction. I'm going to call that my y-axis. What is the resultant vector of these two forces? What is the resultant vector of these two forces? Now, if the car has a given mass, what is the acceleration? Forget about friction. So 450 and 400. And this problem is number 12. So we have a car. This is our vertical direction, the positive y. Just to make it consistent, here's my positive x, and there is a force that is 450 newtons with an angle 10 degrees. And a force of 400 newtons, 30 degrees. So in these are not the only forces acting on the car. In fact, although the problem tells us to ignore friction, but there is a downward force on the car caused by gravity. So gravity should be a force kind of pulling it down like this, right? And which is being balanced out by a normal force the floor exerts on the car, which is upward, which is going towards us, basically. Okay. So the problem is asking us to find the resultant of these two forces. How do we do that? So when you find the resultant, we have to play with projections. I mean, if these vectors represent magnitude of these two forces, to add them wouldn't be a problem. You take, for instance, you fix one of the vectors, like let's say this one, the 30 Newton, you fix it, and then you bring the tail of the second vector, place in the head of the first vector, and transpose it. And then your resultant will be this vector here. Okay. Uh, Here's what happened. I was taken out again, and okay, that's what happened. I was taken out again. My wireless connection went down. Now my ear might be listening, and now you're seeing my entire screen, I think. Okay. So you might be listening now, and you might be seeing my screen. Okay. So those are the two forces, and we want to find the resultants. Here's what you do. I like my students to do this little table because it helps a lot when you want to find resultant forces. This will help you in physics to be as we move on. So what do? You write all forces and you outline them. So I have a 400 Newton and I have a 455 Newtons. And here's my resultant. The resultant is not just 400 plus 450. 850 is not. Because it requires that you sum the projections, right? So we want to find what are the projections of these forces in x and y, and then add them. So what is the projection of the 400 Newton force, the 400 Newtons force, this one, in the x directions? How do I project this force in there? Here it goes. You bring it down from the head of the vector, you bring it down, here it is. So based on the fact my projection of 400 Newtons force, see this head here, points to the positive direction, my projection will be plus the magnitude of it, cosine of the angle between the force and the axis, cosine between the force and the axis. So cosine of this angle here. It's not cosine of 30, it's cosine of this angle. So you must write down that angle, if you will. And what is the projection of these forces in y? Let's do that. You take the head of the vector, bring it on to the axis you want to project. Um, brings on my ear again. I got kicking out. So you have sound, and now you have, you can see my screen probably. Okay. So how do I project in Y? You take the head of the vector and bring it to the y-axis, and then from there we see the direction of the projected vector is the positive direction, is going to carry me a positive number 400 cosine of the angle between the vector and the axis, so cosine of 30. How about 450? So let's project it in x. Yeah, here's the projected direction. Now when I projected my 450 on x, here's what I found. The projection is on a direction that opposes what I call positive. That will bring a negative sign. 450 cosine of the angle between vector and axis. Cosine of this angle here, cosine of 80. Cosine of 80. And the projection in y is going to be positive. See that? Positive 450 cosine of the angle between vector and axis. So what do we do next? We sum these numbers. 400 cosine of 30 plus 450 cosine of 10, or 400 cosine of 60 minus 450 cosine of 80. So the next step is calculator, right? So you go to your calculator, and then we do that. 450 times that minus, no, wait a second, I think I did it wrong. Excuse me. Excuse me. 400 times cosine of 60 minus 450 times 80 cosine equal. So this is equal to 122, more or less. Okay. And for the other one, 450 times cosine of 10 plus 400 times 30 cosine. Uh, 790. So my resultant vector in this case is 122 in the x direction plus 790 in the j direction. That's my r, the projections of it. If I want to find the direction is 5, this angle 5 right here, which is arc tangent 790 over 122. And it's going to be in the first quadrant. And that's how we do that part. So we go to our calculator, take 790 divided by 122 equal, and then we want to find the arc tangent of that. I think that's how we go. So 81 degrees. Okay, good enough. Let me know if you guys want me to do any other problem, and I will work on it. Okay. Okay, I'm stopping taping this now.